Welcome back. We're still in chapter 29 dealing with photons and other related matters. I'll begin this lecture with a discussion of the mechanism by which light can push on things it lands on. When light is incident on a substance, it actually pushes on it. Let me explain how that could happen. I show a diagram of an electromagnetic wave. In the plane of the board, I show the electric field component of the electromagnetic wave. Perpendicular to the electric field, and therefore perpendicular to the plane of the whiteboard, are the B vectors, the B component of the electromagnetic field, which propagates at the speed of light, c. I show an electromagnetic wave encountering a proton. The electric field vector is in the plane of the board, pointing upward. Perpendicular to the electric field vector, and therefore perpendicular to the plane of the board, is the B vector. Keep in mind what you used to know about the electric field at a point in space. In whichever direction the electric field vector points, that is the direction of the push on any positive charge that is placed there. So that charge now is experiencing a push in the direction of the electric field vector, a push upward, which causes it to accelerate and therefore pick up speed. So at some moment in time, that proton is moving upward in the direction of the E arrow. And at the same time, it's in the presence of a magnetic field vector, B, that's perpendicular to the velocity vector. Let's use our right-hand rule to put the thumb in the direction of the velocity vector, the velocity of that proton. Make sure our fingers point in the direction of the magnetic field, and then look to see what the direction of the palm is, in which direction does it face. Well, there's the thumb in the direction of the E vector, which is the same as the direction of the velocity vector. And then you've got the B vector coming out of the board. My palm is now facing me. It's facing in a rightward direction. That's the direction of the force on that proton. It's not so important that we know the direction of that force. It's more important to know that there is a force on that proton when light strikes it. Now, based on this, we have reason to understand that light has a duality, a dual characteristic. It not only is a wave, it travels as a wave, but when it hits something, it hits like light is an object that collides with another, exerting a force on it. So light travels as a wave, but hits like a particle. So in this way, we know that light has a particle-like attribute because it possesses a kind of momentum. Another way to see that light hits like a particle is to know that we've agreed that light has a duality. It's sometimes a wave, other times a stream of particles called photons. Those are the things we can imagine now that are striking the proton, pushing on it. Now, without proof, I'll tell you that we've long known how to calculate the momentum carried by individual photons. There's the momentum symbol. That's the momentum of a photon. And it's equal to Planck's constant h divided by the wavelength of the light that we may imagine contains a stream of photons. I'll emphasize that P is the photon momentum, and that lambda is the electromagnetic wavelength. Now, it was conjectured long ago by a person named Louis de Broglie, I may write that name on the board later, that if this statement is true regarding the particle-like or matter-like aspect of a wave, then perhaps the reverse is true. Maybe there is a wave-like attribute of matter. We twist this equation around and fact, to find the actual relationship between the matter wavelength and the object's momentum. It's the same equation as shown here, except the p's have different meaning. This is a photon momentum associated with an electromagnetic wave whose wavelength is lambda. This is the object's momentum, and that's the corresponding wavelength of the object's matter wave. It's this matter wave that is totally new. It was first postulated in 1926 by Louis de Broglie. I'll write down his name later in a subsequent lecture. Let's use this equation to calculate the matter wavelength, as we call it, the de Broglie wavelength, as it's also called, for a 100 kilogram object moving at 6 meters per second. We have lambda, the matter wavelength, is h over p. P is the momentum. The mass is 100 kilograms. Velocity 6 meters per second. P, the momentum, is m times v, 100 times 6. Final result for P, the momentum, is 600 kilogram meter per second. Now that is what we have in the denominator here. In the numerator goes Planck's constant, 6.63 times 10 to the negative 34 joules per second. Final result, the wavelength of the object's matter wave is very small, 10 to the negative 36 of a meter, which is absurdly small. We have more reasonably sized wavelengths for different objects. The object that we'll be considering next is vastly less massive than that 100 kilogram object we were speaking of. It will be the mass of an electron. That's all for now. In the next lecture, we will be discussing the matter-like aspects, the wavelength of an electron orbiting a hydrogen nucleus. That's all for now.